Hi everyone, I welcome you all in a new video tutorial. In this video, I will discuss the load transfer mechanism in buildings, as this is very important to understand when you are going to design a building manually. For this case, I have taken a one-story building plan as an example. This video is primarily dedicated to understanding load transfer path from slabs to beams. In my upcoming tutorial, I will explain the analysis and design of the beams manually. Before that, if you are new to my channel, please subscribe to it and press the bell icon so you can be notified on my next uploads. Depending upon the bending action, the slabs are primarily divided into two types: one-way slab and two-way slabs. One-way slab is supported by beams on two opposite sides to carry the load along one direction. In this slab, the ratio of longer span to the shorter span is greater than or equal to 2, whereas the two-way slab is supported by the beams on all four sides to carry the load along both directions. In this slab, the ratio of longer span to shorter span is less than 2. The one-way slab will cause slab to bend along one direction, that is, the shorter direction, so the main reinforcement is provided along the shorter direction, the way it is shown. Similarly, in case of two-way slab, the bending action takes place along both directions, so the main reinforcement is provided both ways, as it is shown. Now, let's understand the load transfer mechanism. The load is transferred following the load path from slab to the ground. Now, how the load path is decided? This is decided based on the two methods. One is tributary area method, in which the regular slab area is divided into rectangular, triangular and trapezoidal portions. And the second option is to go for finite element analysis, and which is based on stiffness. So before explaining the tributary area method, let's discuss something about finite element analysis. In this method, the load path is decided based on the relative stiffness of each member in a structure. This means that the stiff member will take more load as it will possess less deformations. Generally, beams have greater out-of-plane stiffness and slabs have low out-of-plane stiffness. So the slab load will be transferred to the beam, as beam provide greater resistance to the deformations. Similarly, beams are connected to the columns and shear walls, which have extremely high axial stiffness compared to the beams, so the load is transferred from these vertical members to the base of the structure. Now, let's understand how the load is transferred using tributary area method. So in this method, the areas are determined by constructing 45-degree diagonals as shown. This would divide the slab area loads to the trapezoidal and triangular distributed load along longer and shorter spans respectively. The load distribution on the beams can be represented in two manners. The one is axial distribution, which is triangular, and the other is equivalent distribution, which is uniformly distributed. And the magnitude of loads along triangular portion is calculated as W naught L in shorter direction divided by 2, and the magnitude along equivalent load distribution is calculated as W naught into L S divided by 3. The W naught in above equation represents the total load on the beam. The total load is comprised of self-weight of the slab, self-weight of the beam, live load on the slab, floor finishes, wall load, sunken slab load, staircase load, which is generally assumed as one-way distribution. Sometimes within two-way slab system, if the ratio of longer span to the shorter span is equal to 1, or in other words, the length and width of the slab is same, in that case the load will be distributed in the triangular manner along both directions. Along longer beams, the load is distributed in trapezoidal manner and its magnitude is calculated as W naught Ls by 2, and its equivalent uniformly distributed load is calculated as W naught Ls divided by 2, 1 minus 1 over 2 beta, where beta represents the ratio of longer span to the shorter span. For one-way distribution, the slab is bisected from shorter direction and it is divided into two rectangular strips, and the load is distributed in rectangular manner on longer beams. In this case, the actual and equivalent load distribution is same, and the load is calculated using following equation: W naught Ls divided by 2. Now the question is, why to convert the actual load pattern to the uniformly distributed load pattern? Basically, these equations have been drawn based on the moment comparison. For example, if there is a simply supported beam which is having uniformly distributed triangular loading at a span of 10 width, so if we calculate the maximum moment, and for that we have got equation WL square by 12, and it will give us 2 kip width. Similarly, if you convert the actual distribution to uniformly distributed load, so for that case, now this load will be 0.160 kip width with the equation which I have just shown you, and for this case maximum moment can be calculated as WL square by 8, and it will also give us the same magnitude of the moment. The analysis of uniformly distributed load is a bit easier than the analysis of triangular. For the comparative analysis, I have taken a one-story building plan. So this is basically typical beam framing plan at roof level, so in which you can see we have got 3 types of slabs, and this is the modeling which I have already done in Etabs. This is how the load will be distributed. In first 3 slabs, S1, the load is being distributed in triangular and trapezoidal manner, whereas for S2, the load is being distributed in triangular manner on both directions because the ratio of shorter span to the longer span is 1. And for the third slab, it is one-way distribution because the ratio is greater than 2 or equal to 2. This is how the load transfer mechanism is followed. To calculate the load along the beams, we need to apply the equations for the triangular loading, trapezoidal loading, and the rectangular loading. Now let's go to the Etabs model and calculate the loading along the beams manually and using Etabs and see whether we are getting the same results or not. So this is the Etabs model in which I have already modeled a simple structure. This is a one-story structure in which the column size is taken as 12 by 12 inches and the beam size is taken as 6 by 12 inches. As far as loading is concerned, so super dead is applied as 30 psf, it is applied as 40 psf. I have also applied the wall load along the beams. At roof level, the wall load is applied along the perimeter of the plan, which is 0.6 kip width, and at the ground floor level, the load is applied on all the beams. Now let's go for the analysis. Based on our schematic diagram, the load along this beam should be triangular and the magnitude of this load should be Ws by 2, where W for the live load we have taken as 40 psf. So it makes 40 into 12 divided by 2, and this is equal to 240 pounds. If we convert this 240 pounds in kips, so this will be 0.240. So let's see what the Etabs have calculated, and yes, it is 0.240 along this direction. And similarly, if we want to verify the one-way distribution, and for one-way distribution along grid 1 at a span AB, the distribution is 0.12. Now let's see whether it is 0.12 or not. We are checking the loading distribution for the live load only, because that's how we can compare our results. We can also do for other loading patterns which we have incorporated in our model. Let's compare for the one-way distribution. So for one-way distribution, our beam is placed along grid 1 and between A and B. So let's say grid 1 between A and B. For the live loads, the loading which I have calculated, it is 0.120, and this is based on the formula which is Ws by 2 divided by 1000 in order to convert pounds into kips. 6 is the shorter direction, W is the weight which is 40, and divided by 2 and divided by 1000. So this makes 120. For B7, if we want to convert our value at B7, so let's see, so B7 is long, so B7 is along grid 2 and between AB, so as you can see, grid 2 between AB, the magnitude of B7 is calculated as 360, and yes, it is 360. So this is a combination of triangular load from this side and rectangular load from this side. So triangular load from this side, this is equals to 240 or 0.240, and the rectangular load from this side, it is 0.12. So this makes 0.36. And in similar manner, the load is calculated for rest of the beams shown in this building plan. Using this load pattern and the equations, we can calculate the load distribution along all the beams included in our model. Now, this actual load distribution can be easily converted into the uniformly distributed load system using these equations. So in order to design our beams, we need to convert the service load into the factored load. So in my upcoming tutorial, we will be designing this one-story structure using manual calculations. If you find this tutorial useful, please do like and share, and if you have any doubt, you can comment in the comment section. For more updates, please subscribe to my channel and press the bell icon so you can be notified on my regular uploads. Thank you and have a nice day.